Hello, and welcome to the final video of supervised learning for this week. Last week we saw how logistic regression can be used to model the probability of a so-called successful binary outcome based on an associated set of covariates. This week we've also seen methods for classification problems that are not binary, when there are categorical outcomes that can take some value k greater than or equal to 3 possible values. In this video, we're going to take our logistic regression model further and meet its multi-class equivalent, multinomial regression. This is another term that we can add to our data science thesaurus because it's known by different names by the various different communities of practitioners who use this type of model. Statisticians will often use the term multinomial regression, as we will here. In psychology, the preferred term for the same model is multi-class logistic regression. In machine learning, it's referred to as softmax regression, and in computer science, it's also known as a maximum entropy classifier. Don't get confused by the wide variety of terms here. Everyone's really talking about the same thing, and it is, in principle at least, not much more complicated than the logistic regressions that we've met already. The central idea of a multinomial regression is analogous to logistic regression. Rather than our outcomes being binary events, they're instead going to be categorical, taking one of a known, finite, and exhaustive number of possible values, which we're going to denote here by the capital letter K. Rather than model our responses as binary random variables, instead we model our responses as multinomial random variables, hence the name of the technique. The multinomial distribution is a discrete probability distribution defined on the set of integers from 1 to k, and has k parameters, p1 to pk. Where for some integer c in the range from 1 to k, the probability pc gives us the probability of our outcome belonging to the cth category. Using this data model, we can proceed to construct a likelihood and a log likelihood function for these k parameters in order to estimate their values and to quantify our uncertainty in their values in the usual manner, based on the sample counts of each outcome. An important point to note here is that in order for us to have a valid probability mass function to use in our likelihood and log likelihood, we're going to need each of these k parameters to be in the open interval from 0 to 1, and also that the k parameters are going to sum to 1. This means that once we've specified k minus 1 of these parameter values, we can deduce the value of the final parameter. We've got k parameters in our model, but only k minus 1 degrees of freedom here. So let's have a think about what this might mean geometrically. We'll consider having 2 or 3 possible outcomes for our categorical variable here, which should be sufficient to see how this idea is going to extend to larger outcome spaces. If we've got 2 possible outcomes, we've reduced our problem back down to logistic regression. In order to have a valid probability mass function here, all we require is that p1 and p2 are between 0 and 1 and sum to 1. This means that they can't just take any old pair of real values, but have to lie on the line segment shown here between 0, 1 and 1, 0. When we have 3 parameters, our parameter space is 3-dimensional, and we have a similar result going on here. We can't have p1, p2 and p3 taking any triple of real values, but these values have to be on the triangle with vertices at 0, 0, 1, 0, 1, 0 and 1, 0, 0. These permitted parameter combinations form a region called a simplex. With 3 parameters, our permitted values are a triangle, or a 2-simplex. With 4 parameters, our permitted values will be on a 3-simplex, or a tetrahedron. I don't have the drawing skills to make you a picture of that one though. These simplexes can also be defined in higher dimensions in exactly the same way. It's just that those are much harder to visualize because they can't be drawn at all. When we're estimating the model parameters, that's the probabilities p1 to pk, we can ensure that these produce a valid probability mass function and fall within the corresponding simplex in at least 2 different ways. Our first option is to simply change the way we write our likelihood function, so that whenever we would have had a pc term in the likelihood, we replace it with 1 minus the sum of all of the other probability parameters. Conventionally this is done by substituting for the final class, so class c equal k, but of course there's nothing special about replacing that probability over any of the others. This leaves us with a model in which we can estimate the parameters p1 to pk-1, or more generally, to estimate the parameters in P without its cth element, and then use these estimates to construct an estimate for the probability of being in the other class, which we've substituted out of our likelihood. An alternative approach would be to use the Lagrange multiplier technique to solve the constrained optimization problem given here. So we're maximizing the Lagrangian expression over values of P1 to Pk and lambda. The resulting point estimates are highly intuitive. They're simply the sample proportions within each category. We can see this intuitively if we consider each class C individually and collapse all of the other classes into a single not C class. This gives us Bernoulli data. I'll leave it as an exercise for you to confirm that this point estimate is correct and to establish the asymptotic standard errors of these point estimates, which would allow us to quantify our uncertainty in the estimate. What we've considered so far is all well and good, but we don't have any predictors in our regression yet. For each response, I is 1 to n, what we'd like to do is allow the probabilities p1 to pk to depend in some way on covariates relating to that response. If we're going to stick to linear combinations of these covariates, we can write this mathematically by letting the probability that observation I belongs to class C be some function g of a linear combination of the covariates, where the covariate values are going to vary between observations, and we allow different vectors of coefficients to apply to each category. We therefore run into the same problem that we had for logistic regression, and we need to consider again how we might pick the function g. We'll explore two motivations that lead us to two different parameterizations of the same underlying model here. Our first motivation for g comes from considering a particular category C and defining the probability of belonging to each of the other classes relative to that category, and we'll do that using a set of k-1 independent logistic regressions. Here again we're following convention and taking C equal to capital K, using the final category as our baseline or pivot category. So in this setup, we're describing the log odds of belonging to categories 1 through k-1 as compared to our pivot category k, using a linear model to make each description. Notice that we've got k-1 vectors in model coefficients, and each of these is going to be of length p plus 1. The exponent of the jth element of the vector beta c is going to give us the factor by which a unit change in the covariate j alters the odds of a category C outcome relative to a category K outcome. Note that we've got k-1 times p-1 parameters in our model here, so if we have a large number of categories or a large number of predictors, then this is going to give us a lot of parameters overall to estimate. One way to deal with this issue is to incorporate additional contextual information about the coefficients that can sometimes give us a helpful way of reducing the size of this parameter space and reducing the variance of our overall fitted model. By rearranging each of these logistic regression models so that we've got the probability that yi is equal to capital K on the left-hand side of the equation, we can use a little bit of manipulation to allow us to see that for the first capital K-1 classes, the probability of belonging to that class is given by the expression at the top of the slide here. And because we know that all of the probabilities must sum to 1, we can then deduce the probability of belonging to the final class. Substituting this probability of belonging to the final class into the other expressions gives us our final expression here, which describes the probability of belonging to each of the first k-1 classes. This gives us our function g, which links linear combinations of the covariate values and the regression parameters to the probability of belonging to each category. Combining the results that we had on the previous slide, we can get an expression for the probability of each categorical outcome for each observation and express that in terms of our regression coefficients beta. This allows us to construct our likelihood function and log likelihood function in terms of the regression parameters beta in an entirely analogous way to what we considered earlier in our case without covariates. When maximizing this likelihood over values for the regression coefficients, we're going to need to use numerical optimization techniques to find the MLE and the Hessian, but this is usually a relatively straightforward task. The most challenging aspect here is to ensure that we're in a part of the parameter space, that is, we have a combination of beta values that gives us a resulting vector p, which represents a valid probability mass function for all of our observations. In order to ensure this, we're going to need to introduce a penalty term here to avoid the areas of the parameter space that are bad in this sense. This penalty term is analogous to our Lagrangian term that we saw earlier, and the idea of penalised regression is something that we're going to return to again later in the course. So instead of considering k-1 logistic regressions, we might arrive at a different choice of g, but an equivalent model, by considering instead k log linear models, as shown here. Note that we're using gammas here to distinguish these regression coefficients from the ones that we used previously. What we have to bear in mind here is that we require our probabilities to sum to 1 over all of the categories, which isn't enforced by this standard model. Adding this property is straightforward though. All we have to do is simply divide each probability by the sum of all the probabilities. This introduces a normalizing term, which here we're calling capital C, which is going to vary between outcomes because it depends on the regression coefficients and also the covariate values for that individual outcome. So adding this normalizing term into our model, we find that the probability of belonging to a particular category is going to be given by the following expression at the top of the slide. Again, this can be used to construct a likelihood function, and numerical methods can be used to obtain the MLE and its standard error. This function might look fairly familiar to some of you. It's called the softmax function. The name here gives you a little bit of a clue as to its behaviour. If the linear combination of the exponent in the numerator is close to the maximum of all the exponents in the denominator, then the function is going to return a value that's close to 1. If the exponent in the numerator is much smaller than the maximum of all the other values, then the function is going to return a value close to 0. So in this sense, it's kind of like a softer version of a maximum value indicator function. The softmax function is used extensively in machine learning and AI applications, for example within neural networks, and it reduces to the logistic function when we have only 2 categories. This lets us see how multinomial regression sits in relation to the simpler logistic case, and also to some much more flexible models. Finally, we can consider the link between these 2 different expressions of the same model by comparing our regression parameters from each. On the left-hand side here, we begin with our linear combination in terms of the beta covariates, and this is going to express to us the log odds relative to category K. If we then substitute in for the 2 expressions in the numerator and the denominator, using our expressions from the second model formulation, then we can do some cancelling within this expression and simplify it down to show that our beta parameters are the difference between our gamma parameters for that category and the gamma parameters for category K. So in summary, in this video we've covered a lot of ground. To begin, we introduced the central idea of multinomial regression as an extension of the logistic regression model that we'd met before. We considered how to fit the model when we've got no predictors, and how we might include those predictors in the model if we do have them. We rounded this out by giving a high-level description of how we might fit the model, and of how we might interpret the parameters in a covariate-driven multinomial regression model. Next week, we're going to delve into some more extensions of the linear model, which have non-Gaussian responses. We're going to be learning about the whole family of generalized linear models. Thank you very much for your time, and I look forward to seeing you in the next video.